Welcome back to Advent of Code 2025, day 10. So we're kind of fallen behind in keeping up with these problems because I had to travel and then I was just too tired yesterday. Uh, so, but I don't want to fall behind in terms of the days, so we'll try and do 10 today and then maybe I'll take a lunch break and then maybe come back and try and finish off 9 because I already started that, and then 8. 9 was a bit of a mess, but with a fresh mindset, maybe I can clean it up. I mean, I have the idea. Doesn't matter. Let's focus on day 10. Hello, DJ. All right, so day 10. It's been out for just an hour and 20 minutes. Factory. Okay, it looks like some sort of optimization of some sort of bin packing problem. Just across the hall, you find a large factory. Oh, where's the music? All right. Factory. Fortunately, the elves here have plenty of time to decorate. Unfortunately, it's because the factory machines are all offline, and none of the elves can figure out the initialization procedure. The elves do have the manual for the machines, but the section detailing the initialization procedure was eaten by a Shiba Inu. We'll let the Shiba off for being adorable. All that remains of the manual are some indicator light diagrams, button wiring schematics, and joltage requirements for each machine. For example, the manual describes one machine per line. Each line contains a single indicator light diagram in square brackets, one or more button wiring schematics, and joltage requirements in curly braces. Oh boy, okay. I was going to use regular expressions for this, but we can manage fine just by pausing it. To start a machine, its indicator lights must match those shown in the diagram. So dot is off, hash is on. The machine has the number of indicator lights shown, but its indicator lights are all off to begin with. Alright. So an indicator light diagram like that means that the machine has 4 indicator lights which are initially off, and the goal is to simultaneously configure the first light to be off, the second light to be on, the third light to be on, and the fourth to be off. Alright. Oh, it's one of these light switching puzzles where each switch does multiple things. Twitch player, have you forgotten how to list video resolutions by size? Oh, is it not offering encoding options? That's weird. Usually it does, but I think at busy times on Twitch they deny that to affiliates and reserve it for partners. It's displaying... Oh, it is showing the encoding options. It's just not showing them in order. Okay. Also, what is 160? 160 is what I'm playing this audio video at. Which, because it doesn't affect the audio. But yeah, 160 is barely watchable. Oh, that's 144. Well, no, wait. Yeah, 144. I guess that's technically lower. You can toggle the state of indicator lights by pushing any of the listed buttons. Each button lists which indicator lights it toggles. Alright. Alright, I get it then. Alright. So button wiring schematic like 034 means that each time you push that button, the first, fourth, and fifth indicator lights would all toggle between on and off. Because none of the machines are running, the joltage requirements are irrelevant and can be safely ignored. You need to determine the fewest total presses required to correctly configure all indicator lights for all machines in your list. You could press the first 3 buttons once each. You could press 1, 3 once, and 2, 3 once, and 0, 1 twice. You could press all of the buttons except 1, 3 once each, a total of 5 button presses. Alright. Hello, Amara. Okay, so first of all, because these are just toggling individual lights, you only ever need to press a button once at most. Like, if you're pressing it twice, it's the same as if you never pressed it, right? So this and 0, 1 twice is obsolete, surely. Alright, so really it's just a power set. We want to find which of these we press once and find the minimal subset. It's just a minimal subset. Well, okay, so we can iterate through all the... I don't know, how big is the input? Well, there's probably ways to be smart about it. It's a bit like a Sudoku. You can find ones which absolutely must be pressed. For example, well, this one's pretty evenly spread, but... second machine... okay, I think I get the problem. So the first part is really just, ooh, okay, how big are these? Yeah, we can do 2 to the power of number of buttons, I suppose. Wait, what's the last thing? Is that... oh, that's for part 2, okay. Okay, I think it's just... really just brute force then. Well, just a bit simpler than brute force because we're not pressing buttons multiple times each. Alright. Oh boy, problem 9. We'll have to get back to that sometime. Just trying to copy some code here. Guess we can solve the problems as we read them in. I could use regular expressions for this. I mean, it's... I can't be bothered to whip out regular expressions. We can just find the square bracket. So Um, so we want I1 equals line dot find closing square bracket, and with that we want that pattern there. So pattern equals line from 1 up to I1. And then light's goal equals a list, and then for Z character in enumerate pattern, if character is a hash, then we want that in our lights goal. Yeah, okay, that's that pattern extracted, and then this bit. I1. So line from, let's say, I1 plus 2 on 2 onwards. Dot split on the spaces, and then we just ignore the last one because that's like something for part 2, I think. So buttons equals that. Let's just discard the last one. Alright. Or just say tokens. Buttons equals... Could we not just eval? These are tuples, basically. Can we just eval this? Oh, no, because they're not comma separated. Oh, that's fine. We'll just, Oh, we can eval that string, and that will give us... Yeah, it'll probably work. For token in... tokens... buttons dot append eval... Just evaluate the string, and that should... be the tuple. Okay. And then let's just see what this looks like. So we've got a lights goal and buttons. So that's the goal, and that's what the buttons do. Oh. Can't have an integer by itself. Let's just... Okay, if you put a comma at the end of a tuple, it doesn't change it. But if you put a comma at the end of these, it fixes it to become a tuple. So we could... Okay, this is a hack. Token and tokens. So... Scrap the last character. Add a comma. And a brackets. That should work. So do we have solo tuples? Singletons? Yeah. Okay. So that's the inputs, basically, and we want to probably do this outside here. Define. So what is the goal? We want to fewest button presses. All right. Define get optimal presses. So we've got a goal, and we've got buttons. We're just wrap this up as a tuple. Okay. And then result 1. Okay. Oops. Okay, right. So now we need to just do this method up here. So we've got a goal, we've got buttons. So I think we just try every combination of pressing the buttons. So, so which of the many cheaty methods in ITerTools does this? It's going to be ITerTools dot let's look this up. Product. No, it's it's none of these. What is it? It's we want without. Hang on. Cartesian product, counter nested. We don't want this number here, do we? Combinations. If I do combinations, so it's combinations, is it? Are in tuples in sorted order, no repeated elements. Yeah. Combinations, but we don't supply the 2. It's just any length. So it's essentially the subset. Let me just try it and see what it looks like. Or for R in combinations buttons in R, there's going to be a whole bunch of text. Combinations missing requirement R. Wait, we need R? No, it's not combinations we want. And I'm still in the browser. Hang on. What? I don't remember what the method is. Maybe it's not even in ititools. Let's just Google this. Python. Get all subsets of a sequence. That's what we want, right? Get all subsets. It's combinations. We have to do it for R in range. I could have sworn there was a... Okay, fine, I can do that. That's easy. But I could have sworn there was a... one function. I guess... Oh, okay, that makes sense. I guess there's no... He didn't add a function that would actually get all subsets Python, because that would be pointless, because in practice you don't do that, because that's exponential. The same reason we don't have... the equivalent of sum for product, because if you multiply like a bunch of numbers together, eventually they get too big. So it's just a silly function to have only for toy problems like this. Okay, so we just do a for loop. For k in range length of buttons +1. We could have all of them pressed. For R in combinations buttons K. At least no assembly problems this year. Well, we don't know yet. I'm sure he'll throw in 1. Botones. Okay, stop. Okay. Let me just... Alright, so the last one is... Let me just look at the last one. Alright, I think that's fine. Alright, so for that combination... Alright, so we want... Best... Okay. 0 is... No, we don't return 0. Well, okay, there's no sensible default. Best equals... length of buttons. Like, in the worst case, we press every button. Is it always possible? Yeah, it must be. Alright, so, and we want to include 0, because it may be that you don't press any buttons, and the goal is to just have them all off. I don't think they'll actually give that pattern, but in theory we should include that. So with that, okay, for B So let's say subset for B in subset. So lights equals what's the best way to do this? Dictionary? Just lights equals I0 meaning the light is off, for I in range length of goal. That's how many lights there are. For B, I'm just waiting for day 12 to take like 5 days to complete. Well, if it takes like 13 days, it'll take us until Christmas Day, so he'd have kept the pattern going. So for B in subset, okay, so we've got a button. It triggers each of these lights. So for running out of variables, X in B, lights X equals 1 minus lights X, or maybe we should use booleans. Is that nicer? Yeah, okay. Okay, so at this point, we want to see if that matches the goal. So, lit lights equals X for X in range. I should really. It's fine. Length goal. If lights X, so the light is on. Lit lights is that. That's a set. If or I don't know. I'm gonna make this a tuple. It's doing it starting from 0, so it should be sorted. If lit lights is goal, so goal, should that look the same? That's sorted tuple, sorted tuple. Yeah, I think so. If lit lights equals goal, then we have a way of turning on the goal lights on. Also, best shouldn't be length of buttons. It should be length of buttons plus 1, because it doesn't really matter. Essentially, this is an invalid best. All right. If lit lights equals goal, best equals minimum of best and length of Ah, okay, there's an optimization here. So because we're looking for subsets in increasing size. All right. Well, anyway, let's just finish this off first. Hopefully next year he can get them all done or get some help. I think he's decided this is going to be the length going forward. And he does get a lot of help, but he wants to always write the problems himself. But he does get a lot of help in testing and stuff. But I'm pretty sure he writes all the problems himself, and I think it just takes too long. He spends months doing this. All right, so oh, I lost my train of thought. Where was it? Best length of subset, right? Yeah. All right, now what we can also do is if k is greater or equal to best, like we're now looking at big subsets, but we've already found a solution which is smaller, then we just return best. Like we know that none of those bigger ones will be any better. And if we go through, if we get here, like generally we're gonna exit early always here, but okay. Okay, that's a mouthful. Probably gonna break. Key error 2. Error 2. X is 2. X 2 is not in there. What? Oh, goal is bollocks. All right. There is a issue here, is that because we are just storing the list of ones we want on, we forget how many lights there are altogether, and we don't actually have a record of that. So instead, we should just have the actual pattern. So let's do Alright, how about we just use the pattern itself, except change it to zeros and ones or something. So lights goal equals, let's say, one if car is hash, else or we'll just use the boolean. Car equals hash for car in pattern. That's simple enough. Get rid of all this. That's the tuple. Alright, so now goal is just like false, true, true, false, whatever. So So length of goal makes sense now. So lit lights is just gonna be... It's just gonna be lights X. Alright, try that. 571. Alright, well... Let's see. If it feels like it's about the right magnitude. Oops. Okay, nice. It worked. Part 2. All of the machines are starting to come online. Now it's time to worry about the joltage requirements. Oh, great. Each machine needs to be configured to exactly the specified joltage levels to function properly. Below the buttons on each machine is a big lever that you can use to switch the buttons from configuring the indicator lights to increasing the joltage levels. Okay, fine. The machines each have a set of numeric counters tracking its joltage levels. One counter per joltage requirement. The counters are all initially set to 0. So, for example, this one means the machine has 4 counters, which are initially 0. And that the goal is to simultaneously configure the first counter to be 3, second counter to be 5, third to be 4, and fourth to be 7. Okay. The button wiring schematics are still relevant. In this new joltage configuration mode, each button now indicates which counters it affects, where 0 means the first counter, 1 means the second counter, and so on. When you push a button, each listed counter is increased by 1. Wait, so are we don't care about the lights anymore? I guess not. So a button wiring schematic like 1-3 means each time you push that button, second and fourth counters would each increase by 1. So you want the fewest total presses. So it's like we're now trying to sum a bunch of vectors of 0s and 1s. So it's oh man. So generating the full possibilities is much bigger now. Okay, so looking at the first example. So 0 wants to increase, the counter 0 wants to increase to 3. So the number of times we press these buttons has got to sum to 3, essentially. So we could do like 3 of those, or 1 of those, and 2 of those, and so on. Interesting. That's a way of, like, breaking it up, I suppose. One way to do this is by pressing 3 once, 1, 3, 3 times. That gets 4 for that, and that adds 3 to that. All right. So immediately, I think a way of breaking this down is to look at. So for example, like I said, with 0, counter 0, we want to make that 3. So we know that these have to be pressed 3 times, like broken up in some way. So for every possibility, every possible way of pressing these, that spawns a whole new subproblem where we've now reached the target with 0. So we delete all those buttons and focus only on what's remaining and what's remaining here. But of course we've got some residual like voltage from those button presses, and then we solve that subproblem. So we're trying to meet that target. So for example, if we press this 3 times, that would hit that target. We cut that off, but we've also added 3 to counter 2. So then we're trying to solve the problem of 5, 1, 7 with those buttons, right? Which is a subproblem. I Or maybe we should start with, just to make the numbers cleaner, we should start with the highest number. So get rid of that counter, because that then we don't have to renumber them. Okay, so if we started with 3, which is that one, we find all ways of pressing the 3's buttons until we make 7. So for each possibility, we spawn the subproblem where we only look at these 3 numbers, and we don't have to renumber, so we can discard these buttons altogether. We're left with these buttons and these targets, and if they're negative or something, then that's actually impossible. I guess I could try that. That seems to be the clearest, like, and throw in some memorization, and let's try it then. So that is that. Get rid of that. So we've got the buttons. And so what was the word they used to describe here? Joltage. joltage goal, I suppose. Joltage goal equals, so it's going to be, take the last token, tokens -1, so that's got curly brackets. Let's just throw in an eval here. So tokens goal from 1 up to -1, so we kind of just take the inner section and then just eval with, we've got an opening bracket, we have the inner stuff, and then throw a comma and that, just in case it's like a single thing. Does it always have a counter for every... Are they listing every every... Yeah, I think so. Okay. Alright. So we want another method here. Get optimal presses. Let's just say joltage. So we've got goal and buttons again, but this time we're gonna like do recursive, I guess. So goal is given as a they're all given as tuples. Okay. 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 My music stopped. Okay, so we want to memorize, I suppose. Let me just print what these looks like. Print goal buttons. Okay, so it's like that's the goal. Those are the buttons. We want buttons to be a tuple, really. Everything should be tuples. Buttons equals... Okay, so we do buttons equals tuple buttons. Okay, so that should still work. Okay. So, yeah. So now we've got a goal. Wait, what? Hang on. I don't think we've got the right tokens here. Ah, we're cutting off the last one, aren't we? Oh, damn. That'll be why. Take that off. Do that. There we go. That makes sense. All right. Memorizations, I don't know how much it will help because there's a lot of possibilities here. Okay, so my idea is we start with the rightmost button and try to hit that target. Oh, I'm really hungry now. Need to solve the problem quickly so I can go get a lunch break and then come back with day 9 or something. So the counter I'm interested in is the last one. So let's say counter equals length of goal minus 1. Okay. So we want to just extract the buttons that involve that counter. Relevant buttons equals that. For button in buttons, if counter in button relevant. Oh, we can relevant button equals, let's say, button for button in buttons if counter in button. So now we want to just brute force all the possible ways of pressing these buttons, I suppose. So the number of presses is exactly goal counter, that number. Okay, so we're allowed to press these buttons, some combination of them, a total of presses times, and work with that subproblem. Alright, what's the Python iter-tools thing that does this? I suppose it's gonna be like let me have a look at the iter-tools stuff. Maybe it's not. No, we don't want to actually iterate over them all. We just want to split the number presses into parts, don't we? Oh, okay. How do you do that cleanly? Probably another iter-tools thing, but there's so many methods here. It's like Python, it's like Get all tuples of integers that sum to a target. What is the is combinations with replacement? Like, let me look at that again. Yeah, but we don't actually, no, we don't want to do that. It's partitioning, yeah, that's what we're doing. Python, so we're trying to partition a number into like specific number of parts. That's what we're trying to do, aren't we? Recursion, I guess we'll have to use recursion. We'll have a whole new method here. All partitions of n with length k with 1 in order of least degrees. Suppose this might length of partitions. Did you beat part 1? Yeah, I've done part 1. Wasn't too bad. Alright, we'll just copy this method because someone's done this partition thing. This is just like a subroutine we want. Oh, that looks good. Except we don't need to... We've got our own memoir. Oh, Python has memoirs built in. So... This was 2013. Alright, let's try this. So we've got a routine here. So we're partitioning a number n into k parts. What's pre? Oh my god, still using X range. Wait, what? Alright, let's not use this one. Let's use a different one. Use this. We don't actually, I don't see why you would even need to cache. Okay. L is the minimum partition element size. So we want L equals 0, I suppose. So let's test this. Print partition. So we want print list of partition function. Say split the number 5 into 3 parts. Just raise stop iteration. What? Length of partitions. Does it just not like me casting it to a list? Should we just say 4p in addition function p? Stop iteration. What? So it did 005. 0 is 0 valid? 0 is a number we want to allow. If k is less than 1. Okay, if k equals 1, if n... What's wrong? Ugh. So it started with 005, that's valid. And then... Wait, no. Yeah, 005. And then it crashed. Let's try another one. Or just write it myself. I think... Why are they raising stop iteration? Okay, let's return. I think this is probably because they were using Python 2 for this, I think. Return. There we go. 005, 014, 023. One. That's not all of them. I don't think this is actually what we're trying to do. Oh, they're looking for unique. Alright, let's just write it ourselves. We'll just tweak this. So alright, this is just generating all ordered partitions. We want unordered, so we need to say... K is 1. That's fine. If for I in range L to n plus 1. For result input... I would think this is right, isn't it? We just don't want to return. Why are we returning? When we yield... Hang on. So... Alright, we don't need L. We're always allowing it to be... Oh, no, we do need L. Hang on. Result in partition function. Ah! That's the problem. Okay, we don't want L, actually. L is always 0. We're always allowed to have 0. Let's take that out. Okay, try that. L. N is greater or equal to... Zero, I suppose. Okay. Do we get all? Yeah, we do. It looks like it. Okay. We've got a way of partitioning a number into parts. All right. So we want to, for P in partition function, the number of presses into length of relevant buttons. Okay. So this will tell us how many times to press each button. So we've got a... So P is a tuple saying press this button once, this button this many times, this button this many times. Okay, so jolts equals 0. Okay, start with that many jolts. For I so P looks like, okay, let's say I num in enumerate P. So I is telling us which button to press. And num is telling us how many times to press it. So we take the button in relevant buttons, so button equals relevant buttons I. Okay. For I don't know, K in button, we want to increase that voltage num times. So jolts K plus equal num. Alright, so if we've done all that, for all of that, then we've basically pressed a bunch of buttons, according to this. And what we should end up with is exactly the right number of jolts for this one counter we're focused on. Okay. So the goal for that counter should be hit. We've got a bunch of residual jolts, and so we subtract that from the goal. Now, if any of the new goal numbers are negative, that means this is impossible. Okay. Best equals none, I suppose. I'm trying to find the fewest presses, so okay. So we pressed the relevant buttons a number of times. We've now hit that goal. Now we need to just call the subroutine on the remaining buttons. So new goal equals, let's say, list of goal up to, and excluding the last one. And then we need to subtract the jolts. So for I in enumerate jolts, new goal, I take away that amount of jolts to see what's left. If new goal is less than 0, oh, don't do that check here. It's whatever. Just subtract all the jolts. All right. If any num less than 0 for num in new goal, then this is an invalid P. So continue. Let's move on to the next one. Okay. So now we've got a new goal. New goal equals, let's say, tuple of new goal. Alright, DIJ, see you later. Okay, so that's the new goal. And the buttons, we got to remove some of the buttons, so... essentially we do this. New buttons equals button tuple button for button in buttons if counter not in button. So we want to exclude all the ones that affect that particular counter, because we never press those again. We pressed them the exact number of times. Okay. So we solve the subproblem. So we now want to call get optimal joltage on this new goal, new set of buttons. I can't think of variables. Z equals get optimal joltage, new goal, new buttons. If Z is none, that means it was impossible to solve. So we continue to the next P. But if we actually got a number, then we've actually found a solution here. So best, if best is none or best is, okay, so num presses equals, so we pressed these buttons that many times. Plus, because that's fixed, plus Z. Z is the optimal solution to that subproblem. Num presses equals presses plus Z. Num presses. Then the new best is num presses. Okay. And then after all that, we return best. We'll make sure we cache this. Hopefully there's a lot of cache hits, I don't know. And then... yeah. Try running it, see? Dict object is not callable. Wait, we've... line cache? What was that? No, it's not cache. What's it called again? I can never remember this. Functools.cache. Alright. Or just from functools import cache. Alright, just try running it then. List index out of range. Wonderful. Ah, because we're trying to subtract. Okay. This particular counter is out of range, so we want to skip that one. So I num in enumerate jolts. I mean, we don't. We don't need to include that one, so for I num and numeric p. If k is not equal to like counter, because we don't actually care about that one. We know that counter will get pressed the exact correct number of times. Alright. None. So if it's impossible, is it always possible? Should always be possible. Yeah, should always be possible. Okay. Huh. There might be some base cases, like if the goal is empty. Like, if all x is 0 for x in goal, then return 0, because we solved it. I don't know if that's something we're missing here. And if it's not, then if not buttons, then that's impossible, because we have to have a button to actually hit a goal. I think that avoided that problem. Why are we doing that? Take that out. Alright, we need to see how much progress we're making here. Are we actually getting results? Okay. We got 45 for the first one. Boy, some of these are gonna take ages. Oh, because these are big numbers. There's got to be a way to... We should really... Be starting with the buttons. Oh. Well, now we're making some progress. How many have we got to get through? 199? We can do it if we just leave this running. It's just some of these big ones. Oh, look at that last one. We've got the 200s. That's going to be nasty. Oh, great. It didn't find a solution for this one. Well, I mean, we've got to try the example input now. Okay, 10, 22. Were those two correct? 10. Oh, next one should be 12, not 22. Okay. Just looking through this again. Jolts equals 0. I num in enumerate P. Okay. Z equals get optimal joltage of new buttons. If Z is none, continue. So that's not solvable. Num presses equals presses plus Z. So the base cases. So yeah, if all the goals are hit, the goal is empty. That's probably what we were having as well. If that's an empty list, then that's also solved. And if there's no buttons, then it can't be solved. Oh, 12 was right. This is not... It's 12, not 22, because this is accumulating. So we actually solved the first two correctly. Okay, that's good. But we couldn't solve the third one. Alright, that's more promising then. Interesting. Yeah, why are we printing? Okay, so... Okay, 10, 12, and then... Okay. So... Let's see how far we're getting into this then. Okay, so... Also, get rid of these two problems. Just focus on that last one. Okay, so... We start with this goal. 10, 11, 11, 5, 10, 5. 10, 11, 11, 5, 10, 5. And we've got these buttons to press. Yeah. And we go for... this last one here. 0, 1, 2, 3, 4. So 4. So we look at all the buttons with 4 in them. There's 3 of them. And we try all possible ways of pressing them. So, for example, if we were to press... I think because of the partition, press this one. Wait, what? 0, 1, 2, 3, 4, 5. Oh, yeah, no. 5. We want to press... We want to hit this target here. And the only button with 5 in it is this one. So we press that one a total of 5 times. So that means 0, 1, 2, and 4 all get hit 5 times. So the goal has now become 5, 6, 6. Like that one's unaffected. 5. So far so good. And then all we're left with is these 3 buttons. We're not allowed to ever press this one again. Okay, that looks good so far. Then we want to hit 4. Hit this goal. So we have to try all ways of pressing these 2. One such way is to press this one 5 times. And if we do that, we hit the goal for 0. We don't affect 1 or 2. We actually hit the goal for 3. And if we take those out, so we have to solve this subproblem here. Interesting. But that's trivial, isn't it? Why is it not solving that subproblem? Oh, hang on. I didn't consider the case where we've already hit this goal. Interesting. So we've already hit this goal. This for loop is redundant, and we never actually do any of this logic. So if we hit the goal, we actually have to deal with it there and then. So if okay, so counter relevant buttons, presses, blah blah blah. Okay, best equals none. If presses equals 0. So it's redundantly met. We've met the target redundantly. Alright. In that case, we don't have to do any of this, and we just say... Basically, we have to say new goal equals that. New goal equals tuple goal that. New buttons equals basically that. We don't have to do this this is always the same. And so is this. Hang on, so take this line out. So we return get optimal joltage of new goal, new buttons. What on earth? Otherwise we do that. Try that. 11! Alright, I think it works for the example inputs. Let's just check that now. So print optimal. Okay, just don't print those right now. But don't print all this stuff. $10, $12, $11. That is correct. 10, 12, 11. Alright, solved it for the example input. We weren't handling edge cases. These edge cases aren't really... Well, they're covered now. Are there any other edge cases? Not really. Like, if this can't be -1 because we're already checking that. Alright, let's do the big one. So ultimately we want these two. This is probably going to take a while. Print 3. I have to start. 45. Oh man. I think it's correct now. I have to wait for 199 things to be done, but some of them are going to take a long time because these numbers are big, and that's not even that bad. Like, look, it gets worse. It really depends on the button arrangements. Look at that. That's going to be crazy, but I don't know. Like, what could be better? Like we might not need to do recursion. Like, we could just fully partition the target. Wait, no. I mean, there's probably a lot of cases where we can see early on that we're going to exceed We've done 8. We need to do 200. I don't know. I'll just leave this to run. I mean, what else can... I would like to know which line I'm on. I do that. It doesn't matter, we'll just let it run. Are there any particularly trolly ones? See, these were all numbers under 100, and now we're getting bigger numbers down here, so this is going to be a problem. Okay. Well, I mean, it looks like this will work. So we're on 10 right now. That's some big numbers, but... So 9 was instant, even though the numbers are big, but I guess the button arrangement... When you have singletons, that makes it a lot easier. Alright, I mean, what could actually be done to optimize this? Maybe... Like, when you see things like 4... I don't know. When you see singletons... but you don't always have singletons, so there's no point worrying about singletons. Like, maybe you should start with the counter, which has the fewest number of buttons. Because then you're more restricted. Not as many branches, I don't know. This is kind of like an algebra problem. We're trying to see how many... Like, if we took a number, say 100, or okay, so let's look at this last problem. There's 225, so we know there must be at least 225 button presses. And minimum 225, maximum sum of all these numbers, essentially. So we know the correct answer is between 225 and the sum of these. So for a given number, we could partition that number into the number of buttons, but that's too many. Partitioning is what's expensive, so if the reason doing this is because it partitions into a smaller number of buttons. So trying to isolate one particular counter and then take that out of the equation. Oh, this is taking a long time. To get to 200. Could I run and get a sandwich? And come back and have it still run? We're stuck on this one with this. We're building up a massive cache, and maybe that is a bit of overhead that we don't need. Like, what are the chances specific? Set of golem buttons comes up again. We're probably not getting many cache hits, so building this gigantic cache is probably costing us. let's stop. Don't use the cache. Stop using cache. And we'll also print what line number we're on as well. Let me just see. Okay, also. Okay, for line in enumerate f.read lines. All right, we'll just use the line +1 so it matches the IDE. All right, try this. No cache. Guess no gym for me tonight. They hadn't plowed the parking lot. Oh. Okay. Alright, so I've removed the cache. I think the cache was pointless. Let's see if that actually speeds things up. So the first one takes a while. 20 centimeters. I think this is going to take a long time. I don't know what... I've already written this. So this works. It's going to take a long time to get through all the lines. Maybe we do need to cache. But we should reset the cache per problem, because why are we reusing caches from different problems? I think that's pointless. Okay, we're getting somewhere. We're on line 9. Got to do 200. So it's the problem is when there's lots of buttons. So when the numbers are big, that's not too big a deal. The real issue is when there's lots of buttons. Like, if you're being greedy, generally you want to press the button which has the most numbers in it, because you're trying to fill this goal, and like hitting the big buttons adds more joltage overall. So maybe what we should be doing is turning this on its head and saying, take the biggest buttons and try every possible number of presses on them from 0 to, I don't know, one of these numbers. And then take the sub-problem where we remove that particular button and modify the goal. Yeah, maybe that's the better way to do it. So we're doing this partitions thing. I feel like we can also finish early when we see that we can't beat a certain target. Like, so here, get optimal joltage. I don't know. I think we just leave this problem to run then, but... Do I just leave the stream running? Let's see. So we're on 10. 10 is taking a while. That's because it's got lots of buttons. So the problem points are going to be these ones with lots of buttons. There's lots of them. Either I just stop the stream and just let it run, and then I just like record myself entering the answer into the website and then stitch the two videos together or something. I do want to try this different approach. I don't want to stop execution now. I think the approach really, we should be greedy here. We should be going for the biggest buttons and then leave the smallest buttons for last. Like, you get the most value out of pressing a big button. So you should be doing that. What do I do? How long is this gonna... what is the estimate here? So we've completed 10, so that's like 5%. It's gonna take a long time. It's been several minutes, so... Yeah, I can't finish this on... I can't let this run to completion on stream, that's for sure. So either I stop and try a different thing, but we've proved that this gives the right answer. So I kind of just want to let it... Okay, how long is 10? Let's see how long 10 takes, because this is... If there's some which take like an hour on their own, then this is not feasible, and it's not even a good solution. I'd rather find a better one. 10 is this one, so it's like lots of tuples, but that does actually happen sometimes. Let's wait for 10 to finish, and if it doesn't, I'll have to come back later with problem 9. Alright, I'll stop the stream there. I'll leave it running. I'll just record in... If it's the correct answer... Well, I'll record myself typing it into the website, and if it's the correct answer, that's it, we're done. I'll just upload the video or whatever. And if it's the wrong answer, then I guess we're gonna have to do another stream, aren't we? But there's no point me sitting here any longer. I need to go eat, and then later on I can try and do another stream where I catch up on problem 9. We're so behind. There's only 2 more days after this. I want the final day, we only have to do the final problem. this problem 10 is a real problem. I want to see at least 10 get done, so that will give us an idea of whether it's doable. Problem 196, that looks quite nasty. That's the biggest one. No, it's not. 122 is worse. Oh boy. The numbers aren't too big though. 68. Alright, there's nothing more for me to do here. Let's just stop the stream. Don't really want to raid when I haven't even solved the problem. No. Okay. Alright, well that's it for now. I'll probably come back later with a stream for problem 9 or this one if this one failed. I think this will work though. I mean, it's... I don't see anything that's fundamentally incorrect here. It's just really slow and it's just trying a lot of values. Alright. See you next stream. Bye-bye. And welcome back. Oh, okay, my kettle's really loud now. Let's carry on with this problem. So, okay. We're really behind in the days, and if I manage to finish day 10 today, unfortunately, I don't think I can really catch up on the past days 8 and 9 because it's the evening. It's late evening now, and I just don't feel like coding in the late evenings. So tomorrow will be day 11. Maybe we can fully catch up on everything. I don't know. Anyway, let's see if we can manage to finish off 10 today. So I ran this program, which I think is giving the correct answers. But it's been hours now, and it's only up to like 13, so clearly it's too slow. And I'm just going to stop the process there. Let's save this progress, just in case it's of use to us, but clearly we have to write a new algorithm. This doesn't work. So copy that. Stop. We can let the jet engines cool down before we charge them up again. Maybe we could just make a little scratch pad here. Just temp.text. Paste them there. So that's what we've got so far. If we write another algorithm, at least we can compare them with these numbers we got here. Alright. Is my laptop cooling down now? It's been running like this for hours. Problem 14, it seems, is just not doable. Okay, so I did think about it a bit, and I kind of realized something. I almost spelled out a potential solution without realizing it. It just hadn't occurred to me. So I was pointing out this observation that if yeah, let me think for a moment. Oh, I'll get my tea. It's kind of like the coin problem, where you're trying to choose the minimum arrangement of coins to make a number within the coins at different denominations, and that has a dynamic programming solution, but the dynamic programming solution doesn't work here because you can't quite isolate subproblems away from each other like a polynomial number of subproblems, because the reality is the number of subproblems you have is always going to be basically like the order of magnitude will always be something like these numbers multiplied together, because there's no real way around that. With the coin problem, it's different because there's just one total. So it's one number. Alright, but I did say something that was really valuable, and that was the observation that in general, you would like, if you're being greedy, you would like to pick these big buttons first, right? Because they add the most value. You're getting 1, 2, 3, 4, 5, 6, 7, 8 counts every time you press that button. And like your goal is to get this all up, right? So in general, you would press this as much as possible. Now, you could press it the maximum number of times until one of those is full, but that doesn't necessarily mean it's possible to finish after you've done that, so you can't just do that. The greedy algorithm probably doesn't work. I think I can find a counterexample pretty easily, because you then make it so that if there's ties here, you make it so that other buttons will go over the limit or something, I don't know. But I mean, this observation that you want to go for large things first can be realized by I mean, basically what we're describing is A-star search, aren't we? Where the heuristic would be number of elements in the button, because that makes the most physical distance to the goal. If we're judging distance by like the Hamming metric or whatever, and we're searching through a search space where the search space is just all nodes with all vectors of this many integers, and the goal is that number, right, that vector right there, and the neighbors are basically each one of these, which node you're taken to from there. So like this gives us a neighbor where you add 1 to 2 and add 1 to 6. And yeah. So maybe his A-star search is the way. Because I reckon a lot of the time, even though it's not technically correct to pick the largest buttons as much as possible, then I think in general, if you press the big buttons a lot, you will get to the correct answer, roughly, and you won't have to backtrack much to actually get, even if it isn't correct, you won't have to backtrack much until you do get to the correct answer. So I reckon you should be favoring the big buttons. And A-star does that. So I think this is an A-star problem, really. This yeah. So maybe we do that. So let's try it and see what kind of numbers we get. And it may well still take a long time, but I don't think it'll take as long as this recursive backtracking, whatever it is I did. I don't think this is really going to work. I did think of a different thing, which I thought was dynamic programming, but then I realized it would still be exponential time, which was to kind of like take the first K buttons out of these buttons, and you do some sort of dynamic programming where you try to solve with only the first K, and ultimately you're trying to solve with all of them, but you first solve the problem with the first K, and then add this in and solve it. Ultimately, I think whatever that was, it's still going to be exponential time because there's still like this many different states, different goals. This multiplied together. I don't see any way around that. I think this could also be an LP problem or an integer program. Ooh, hang on. What if we use... What was it? Z3? The thing that we used before in one of the previous problems? This could be an integer programming problem. Like, what are we trying to do? We're trying to choose... We're trying to minimize... So we're trying to choose... We're trying to choose a... Oh man, this... Okay, this is actually starting to look like we can set it up as a Z3 and just have Python do it. We're choosing a... vector of integers such that the dot product or the vector sum or whatever, I don't know the terminology, will equal, strictly equal that. What are we trying to minimize? We're trying to minimize the raw element-wise sum of that vector. That's completely an integer programming problem, isn't it? Okay, so I was about to code a star search. I feel like throwing it into Z3 might actually be better here. Let's see if I can remember how to do this. And then it will do whatever it does behind the scenes, like linear programming, relaxations to get approximations, and then rounding and all that clever stuff it does behind the scenes, which I used to know back in the day, but now you just let libraries do it for you. Yeah, okay, so we've got two potential approaches here. Let's try this. Z3. From, what was it? Z3 is, where's Z3 from? Install it, don't you? Install and import package Z3. Let's do that. So let's minimize this. This is just no good. Oh no, not this one. This one. Let's try new. Define. Get IP solution. Goal buttons. Okay. All right. Z3. I don't remember how to use Z3. Let's look up a tutorial or something. Alright, let's just have a look at some guides, remind myself. It'll probably come back to me. Once we look at this stuff. Oof, light mode. Z3 import star, yeah, let's do that. 3. Okay, so integer variables, so we want to create like basically constraints equals what is... Alright. Solver.add constraints. So can you just add them one by one? Let me just copy this in just to give me some assistance here, but I'm not using it. Alright, let's figure this out. So I want to... Okay, so we'll say x1 through to x something is the number of times we add each of these, right? So it would be... What? Okay. Say for k in range length of buttons, x how do we... Hello, MBZ. Welcome in. Learning how to make your own Wheel of Struggle submission. No, but wait, wait. Are you referencing something with that? Was there a submission I made before which looked like this? What we're actually doing is to describe this. Oh, are you learning how to make a game? Oh, make an actual game. Ah, okay. No. Well, at least I hope not. We would, if I was, this is not a game we would want to play. It's basically... Oh, it's kind of like those, you know, in puzzle games where you have a bunch of lights and there's like, you know, if one switch controls these lights, like maybe these 4 lights, and toggles them, and then another switch toggles some other set of lights, and you got to turn them all on. It's basically that, but on a massive scale and horrible, and not even can't really do it by hand. You need a computer to do it. But yeah, it's basically that. We have a set of like values we want to reach, and we have a set of buttons which increase. So this oops, that button there, the buttons in brackets, says that if we press this button, it will add 1 to light 0, light 1, light 2, light 3, and light 6. Or alternatively, if we were to press this button here, it will add 1 to light 4, 5, and light 6. And the goal is to find some combination of buttons that will make light 0 exactly 54, light 1 exactly 55, and so on. We have to hit exactly that target. So we've got to find an arrangement of buttons to press. But not only that, we've got to find the minimum number of button presses to do as well. To do that. And we've got to do it basically 200 times for all of those. And I'm having a lot of trouble doing this because the last solution I wrote earlier in the afternoon, I started running it and then I left it running for like 4 or 5 hours, and it reached as far as number 13, and I've got 199 to get through. So that wasn't fast enough. So yeah, that's what I'm trying to do. Yeah, it's not a game anyone would really want to play on the Wheel of Struggle, but it is a struggle. But now I'm recently realizing there is a sort of a library in Python, which some call it a bit cheaty, but I mean, the point of programming is to be lazy and to get code to do things for us. So I'm going to try and using that. It's called Z3. It's basically a clever, it's not like AI, it's deterministic, so it always does the same thing every time you run it, but it's sort of a smart system for solving equations similar to that. So if you just plug in, you just tell it what my constraints are, what my values are, what I want, and then let Z3 sort it out. Z3 will hopefully spit out an answer. That's what I'm trying to do now. And it means we don't have to care about what Z3 is doing behind the scenes. It's doing some complex algorithms, sometimes involving geometry, where it's trying to draw lines, find the crossing points, and find the optimal way of arranging things, but it's something we can just kind of give to Z3 and let Z3 figure out. So that's what I'm trying to do now. So the language we have to use is we have to tell Z3 what our buttons are. Where did I write this? Here, okay. So we need to tell Z3 what the buttons are and what they do. Why did I write this here? Take that out. Alright, this code is all trash. We can just hide it because I don't think it's just too slow. Writing from scratch now. So for k in range, so for each of the buttons, from 0, 1, 2, 3, up to the number of buttons, I guess we want to create a thing called variables. We create a variable for the button. I mean, the nice thing about Z3 is it's not, you don't really need to know much programming to use it. You're mostly just kind of, you just need to know the barrier between how we describe things to Z3. But you don't really have to write much code other than that. So we're telling it, these are my variables. So I want to say variables.append. Ints. Let's just say X. Hello, Amaro. For a second, I thought you were still streaming since earlier. No, I ran my program. I left it running. I went out for lunch and then got distracted by things. And several hours later, I came back and I only got as far as problem 13. In fact, problem 14, I think it's just pretty much unsolvable with that recursive algorithm I had before. So I've scrapped that. I'm going to try using Z3 now. Because I forgot all about Z3, but Z3 was something I discovered through Advent of Code a few years back, and it's kind of like the integer programming solver. I think it might be able to just do it. I left a brute force solution for part 2, and 9 hours later, it wasn't done, so I'm trying again. Yeah. Was your brute force using any kind of memorization or anything? Like, I turned off my memorization because I thought it would actually just slow things down. But maybe I was wrong. Maybe I should have left it on. But just delete the cache after each problem. I don't know. But I'm probably not going to stick with that approach anymore. Hello, Slinky. I'm on problem 10. Even though problems 8 and 9 are not done yet, I'm just trying to keep up with the current day before I... So I am falling behind, and tomorrow I'm going to have a huge backlog to try and fit in if we're actually going to finish on day 12, but I don't know if that's going to happen. 10 is an interesting problem. I'm trying to use Z3, so if this works, Z3 should just solve the problem for us. It's an integer program solver. Ints. Ints. It doesn't like ints. What's wrong with ints? Alright, I need to look up a up-to-date Z3 guide. I think it's just out of date. Z3 JavaScript? No. It's on Z3 Python. Alright, here we go. Sorry for the blinding white mode documentation. It's int. I guess, do we need to give it a name? I'll give it a name anyway, I suppose. Could try 8 to at least get all the silver stars. Not tonight. It's like the evening for me now, and I just don't feel up to any programming. I think if I manage to get 10 done, I'm just going to go play San Andreas or something. Int. Z3. We've imported it, right? Z3. I don't think this is how we do it. Hang on. No, don't do it like this. Just say x equals int it doesn't recognize int, but I should have imported it. Z3. Let me have a look in the modules. Maybe it's not actually called Z3. Maybe it's Z3 solver or something. Or I just look up a previous Advent of Code where I actually used it. Wait. No, not plugins. What's it called? I don't remember how this works now. They've changed the layout of this. Project settings. Hang on. Wait. I can't even find a thing called project settings anymore. Where have they put all this stuff? Project settings. I'm right-clicking on the project. There's nothing called project settings anymore. Python packages. Okay. Boto pip z3. Backup ZFS snapshots test 3. I don't think this is right. Uninstall that. I think might be Z3 solver. Where's the market? How do I... Z3, is that just like something S3 related to the storing things? Right, how does this work? Search for packages. Okay, Z3 solver. There it is. That's it. Well, I'd prefer to use the whatever it's called, the built-in marketplace thing, just to make sure I'm getting the right one. Yeah, I could do that. All right. So okay. Variables.append int x. Just, I don't know, just just give it a name. So x1, x0, x1, 2, so on. All right. So we've created variables for the buttons. Now what? Constraints. So one constraint is that every x is greater or equal to 0. Constraints. For k. How do we add a constraint if we don't know the name of it? I've got a variable number of variables here. I don't know the names of those because it's like they're anonymous. But we do have pointers to them. How do I... All of this documentation is assuming we know the names of them. List comprehend. Oh, okay. Here we are. All right, let me show this. This might be a bit more useful. Okay, so yeah, we're doing something like that. Okay, fine. So my X is this, essentially, but... So X equals, let's say, int... Oh god, that's an ancient way of doing it. Even dot format is not really used anymore, but I just like to use it. Int dot format k for k in range length of buttons. All right. So that's my x vector. We're trying to find the solution vector x. And we want the so for each of these buttons, we need to build a matrix, don't we? We need the first row. So there's going to be a binary matrix where each of these buttons is a... Why can't you treat this as binary? I already am. But the number of times you press each button is not binary. It's because you have to reach these targets, which are like unbounded integers. But each button is binary in the sense that it adds 1 to these specific counters. Oh yeah, I'm doing part 2. If you go to the website and you haven't solved it, you only see part 1, where it is actually binary. Yeah, that was an easy part. I've done that. If you solve part 1, you unlock part 2. So it's no longer the lights puzzle. Now it's more of a algebra puzzle. You're trying to sum these algebraic expressions to get exactly that vector there. And each button adds 1 to each of those. The light status is actually relevant in this one, yeah. So this is an integer program, definitely, and I think Z3 will actually solve it. I'm trying to understand how to... Okay, so that's the x vector. Now we need to make a matrix, I suppose, where each row is going to be just zeros and ones, and it'll have length like this, and each button will contribute 1 row where it'll be a 0 or 1, depending on these numbers. Oh, don't move things around. Oops. 0 or 1. And the goal... Wait, is this right? Yeah. And we want our constraint is that this matrix pre-multiplied by x, this vector x, equals the column vector, which is this goal. Yeah? Is that good algebra? I think so. And we also want x to be positive definite, which means it's all non-negative values. That's also a constraint. But those two things I've described are the most basic algebraic expressions in like linear algebra. So hopefully that's actually all right. So what do we do? How do I make a matrix? So we don't need to use numpy. Well, we could use numpy, but we don't need to use numpy. We can just use lists of lists. 3x3 matrix of integer. Okay. Or should I use numpy? I think maybe I should just dig up the Advent of Code problem I did before, because I'm pretty sure I did something like this. Using Z3 with numpy. Let's just carry on as I am. It might be fine. Using backtracking plus pruning now. Alright. Let's get rid of that. So the matrix, let's call it A equals empty list. And then for button in buttons row equals, it's going to be 0 for, all right, let's just say n equals length of goal. That's the size of all our vectors. And like length of buttons is a different length. Button row equals 0 for range n for the w in button row w equals 1. So that's a binary row. Pop it onto the matrix. So we have a matrix. We have an X. Now, one constraint is, okay, how do I... Maybe Z3 is overkill. This is actually... No, Z3 is probably... No, because it is integer, an integer problem. If it was a linear program, we would like have fractional values and stuff, which is not what we want. Z3 is the lazy way, yeah. That's what, yeah, that's good programming. All right, so can I just say something like x greater or equal to 0? I don't think it does like vector stuff like this. What does it? I mean, Oh, there's actually an easier way to do this. We can do this. That just does what we're trying to do, but that's gonna be length of buttons. Equations. I'm just looking at a bunch of guides for different things. Oh man, maybe I should dig up that odd Advento code problem. I think it was like a physics type problem. I mean, this might just be right as is. Maybe we just leave that. All right, x is greater or equal to 0. That's a constraint, but we need to put it into. Okay, so we've got S is solver. Okay, so we create a solver. And then we do s.add the constraint that x is positive definite. Okay, that's the easy one. Let's try running that, see if it breaks or anything. No, stop. No, it doesn't like that. Alright, how do I tell it that? This... sure someone solved it in 10 minutes with 5 lines in Python. Yeah, I wouldn't be surprised. X0. Alright, well, we know we can do it this way. We can just say... Okay, create the solver to begin with. And for k in range length buttons s.add x k greater or equals 0. Okay, fine. That is a constraint. And then, what about this matrix? Do I just have to write out the full matrix? Like, I don't think we can just tell it how to multiply matrices. We have to write out the row. So part 2 is just hitting the buttons with each wiring, adding 1 to the total output. Yeah, for each of those lights. Well, they're not lights anymore, but for each of those counters. Ooh. Oh, okay, we can use list comprehensions this way. We can do this instead. What? S.add x greater or equal to 0 for x in x. Okay, we can do that. Alright, don't worry about matrices, we can just do it row by row. So we can say, the button in buttons, row is that. Okay, so we've made the row, don't put it into a matrix. I'm sure there is a way, because I think I've done it before, but let's just say now we do the dot product between okay. So we want just sum of x row k times row k times xk equals goal sum of row k times xk equals goal k. Is that right? Equals. Yeah, but is Z3 gonna understand that? I don't know what Z3 does or doesn't understand. And no, that's wrong. Hang on. K in range n. So the dot product of row with x equals that element of the goal. And that's wrong. Hang on. No, it's not k. No. It's hang on. I gotta think this through. Oh, this does go inside there. No, it doesn't, does it? Hang on. Oh, no, we're not. Okay. If we look at each element of the goal from 0 to n minus 1, for that element, we're saying that for every button which affects that particular counter, if you add up the number of times each of those buttons is pressed, it should equal that row, right? That element of the goal. How do I put that into words? So for button in buttons, okay, take that out. So it's like a linear equation, yeah, except it's an integer equation. That's the only reason I can't just plug it into an LP solver, which would actually be efficient. IP solvers do smart tricks to try and speed things up, even though they're technically exponential. But it is actually a linear equation. The only thing which is confusing me is the language of Z3, but like once you get the hang of it, it shouldn't actually be that bad. All right, so we've got we understand what the buttons are, and we've put them into a matrix or whatever. Let's just just put them in here. Okay, now for k in range, not buttons, let's just say I in range n. So that is for each goal element. So I'm going item by item here. I've got 44 here, and I want to. My constraint is that each element of x multiplied by the 0 or 1 value of whether it's included in that button, that dot product equals that number 44. That's what I'm trying to say. All right, okay, that makes things clearer now. So I'm trying to say sum of, so it's x k times so it'll be the kth row and the ith column is that right? And that's I. That's so confusing. I should be drawing a diagram of this, but okay, that looks, so AK is basically like the kth row of this. So it's for each button from each of these rows is a button. The ith column always corresponds to 0 or 1 for whether that particular counter is affected. And I is the counter we're interested in right now. So that counter is the column. And we're going through each of the rows, taking the 0 or 1 value and multiplying it by xk, summing all those values, and it should equal the goal. Could try this. Is that a valid constraint in Z3? I mean, it looks like it's all made up of primitives, so maybe, I don't know. So that is the constraint. That's it, right? Nothing more. It's actually a very simple. It's as simple as IPs get. Integer programs, like everything is greater or equal to 0, and everything sums to a particular value. That's what we're saying. Okay, the last thing we need to tell it is we want to minimize. Oh, for Z3 we need to have capital S here. Because we're using the Z3's understanding of sum. Okay, oh, how do we... Oh, and we're trying to minimize. What's the language for that? Solve. Solve. Also, we should be... It's not a solve. We're not trying to find a solution. It will work, but it won't find the minimal solution. We actually need to change it to optimize. To do a minimizer. And then finally we need to do s.minimize. Is it sum of x? All right, and then we could just copy some of this code. If it's satisfiable, which it should always be, hopefully. Model equals s.model. Minimized. X. Wait, what does this mean? So how do I get... X out of it? Do that. No, we're not trying to minimize X. We want to model. What are we trying to do? Yeah, we're trying to get the value of X. Just say X. Let's just print it and see what happens. The 3 exception. All right, fine. Just what's in the model? Just tell me what you've got. It seems like it solved it, but print. Print model. Just what's in there? Model dot. Okay, just print the model. So those are the values. Those are the integer values. Okay. How do I extract those? What is that format? Model. For the k in model, print model. Is this an iterable? Now I gotta look at this documentation again. These guys don't really tell me what I want to know. How do I get the answer now? It's there, it's staring at me in the face. You index into the model. Okay, what's the index? Solved model. Okay, fine. For K in... Oh, why was I printing model? That was the... Go on. Okay. Okay, okay. No, but I want to know the value. Okay. Okay, okay, do this. Model. There we go. There's the numbers. Have you tried optimized linprog from SciPy? SciPy. But that's a linear program. So it will give you fractional values. Which, I mean, you can use that to, like with rounding, to try and find a close integer solution, but it will give you like 0.7 of this and 1.3 of this. It will use fractional button prices. I mean, there are special problems where it just so happens that the solution to the linear program might actually coincide with the integer program. I don't think that'll be the case here, though. I think the actual linear program solutions will probably be like fractional values. But it could work. I mean, there's a whole branch of science around using linear programs to estimate or get close to the true solution for integer programs. It's like a huge field of research, but I don't remember any of those methods. And that's actually what Z3 is already doing, essentially. It's just doing a lot of those clever patterns. Okay, we just return the sum of... Okay. Return... Okay, fine, just do return sum of model K for K and model. There we go. Let's try that then. No, what is it doing? It's still in Z3 language. How do I... Well, I don't know, cast it to an int? Or get value or something? Model K dot as long. Okay, as long. Get it as a long int. Oh, that ran fast. 45, 68. How does this compare with our 45, 68, 46, 58, 92? 204. That's as far as we got with the... Oh my god. This could be it. That was instant. Oh my... This is exciting. I mean, it coincided with the values for that, so this better be right. And even if it's not, I think it'll only take a couple of tweaks to fix it if I've made a mistake somewhere. Yes! Z3. That's how you cheat with style. But that's what you do. Z3 is used in research and industry for a reason, because it's good stuff. And by all means, it's good to practice using it. That was so fast. And it's because it's such a regular looking integer program. That's like the quintessential integer program. It looks so much like a linear program, and it has the most basic constraints. Everything's positive definite. This matrix pre-multiplied by this vector, whatever, equals exactly this vector. That's as basic as it can get for the formulation. So, it knows all the tricks. And I used to know some of those tricks back when I studied nonlinear optimization, which was a tough course. Can you go over the code again? Yeah, okay, so so you want to see the Z3 related code or just everything else that is working outside it? And there's not really that much outside of it. So the Z3 code. So we've got our goal for what we want the counters to look like as a tuple. Z3 code, yeah. Okay, so the buttons comes in. So it comes in this form. The buttons are a set of tuples which just explicitly say the indices. And the goal is a tuple which looks like that exactly. So the Z3 language, we create this int vector, and it's basically the number that's pre-multiplied by each button, i.e. how many times we press each button. X is a vector that describes how many times we press each button, so it has length. We should have said m equals length of buttons, so it has length m essentially. And then in the Z3 language, we want to use an optimize. You can use solver. So if I wrote solve here, solver, could try that, solver, and do solve, it will just find a x value which works, which may be what you want, but it's not going to find the best one, so it'll just be like solver dot s dot solver. No, it's not. It's s dot. Let me just look this up. I'm interested to see if it's s dot. No, you just say solve. Solve. No, wait. What is S? S is solver. I've got to look at this. Alright, doesn't matter. But you could write it as a solution, which you'll just find a solution, but let's just leave it the way it was. Unless you just change this word. Let's see what it comes up with. Dot. Dot solve for. Yeah, it's probably solve for. Oh, it doesn't. Okay, whatever. Doesn't matter. There is a way to do it. And in theory, it should be easier because it's not trying to find the best. So we've told it to use the optimizer. Then for each button, we want to specify that x is greater or equal to 0. So if we took this out, and we're allowing x to be negative, let's see what happens. Does it come up with better values? Yes, so it found a better solution, 55 than 68, where you're allowing negative presses, which could work if you're subtracting voltage, so you can remove that vector voltage instead of pressing it. So you have to add that constraint. So x is positive definite, and then I created for convenience, but I'm pretty sure there's a way you can just make A as a matrix, and then you just tell Z3 that I want this matrix multiplied by this vector equals this vector. Then we don't have to write all this long-winded stuff. We do have to create the matrix, but then we don't have to do this for loop. We just say there's one constraint, A times X equals M, or whatever. I just don't know, these guides are not clear because they've dumbed it down a lot. And it checks for satisfiability, i.e. whether it's possible, which it should always be according to the input. That line there is probably the most confusing, but it's really just tying every X to the corresponding button boolean, whether that button contributes or not. Adding up all the presses of each button, and that should equal the number of presses specified in the goal. That is done on a row by row basis. And then we tell Z3 we want to minimize that expression there. But there's a lot more ways you can tell Z3 to do stuff. It's quite clever. You can tell it to, so there's a command called simplify, so you can tell it to simplify expressions. You can tell it to, what else? Or you can use real vectors, Boolean vectors. You can tell it to solve logical equations. Yeah, I'm looking at the advanced topics stuff here. There's all sorts of stuff you can do. Yeah, like basically before AI became something which could solve these problems just by pasting the problem in, which is now the case, Z3 was the most cutting edge way of solving problems the lazy way. And it's allowed. Eric's aware of Z3 and he's actually pretty happy people use it because it's different from AI because it's deterministic and it has a set formula and set tricks that it uses, so it's not hiding anything or it's not just finding solutions. It knows. It is following a process which is repeatable, so it's all fair game. It's actually calculating, not doing probability guesses, yeah. Well, I mean, yeah, well, okay, no, deterministic is probably, it probably is deterministic, but that is not a requirement. Like, it would be fine if it wasn't. I guess determinism doesn't matter. Like, there are algorithms where you use random numbers, like quicksort, for example, to get solutions. That's absolutely fine, I guess. I guess what I meant really is that the process is not obscured. Like AI, you've no idea what it's doing. It probably just found a solution that someone did before and is working off that. So yeah, some of these problems, Z3 is pretty good. The last time I did it, I can't remember when it was, but it was like for a physics problem with lots of asteroids moving about. You had all these equations for the speed and the velocity and the positions of the asteroids, and you had to find where they all collided or something like that. And it was quite hard to like from first principles, but Z3 became a bit of a meme. A lot of people just used Z3 for that. Can't think of a fast way to do this in GML. I have to write Z3 myself. So because this is a very regular looking LP, it probably uses a standard LP relaxation technique, which is not too difficult. So you could try running it through an LP, see what you get, and it could be the case that you just have to round it to the nearest integers or something like that, and it might actually be the right answer. I wouldn't be surprised. LP rounding is a valid way of solving problems sometimes. I think because it's so regular looking, and there's probably some pretty basic algorithm it's using. I don't know. I was gonna write A star for this, and then I remembered Z3. I think A star is probably better than like any recursive backtracking technique, because A star is, the idea would be that I would prioritize going for the big buttons, which I think is what Z3 is doing anyway. It's probably prioritizing the big buttons. And when you hit a dead end, start trying the smaller buttons. Alright. Well, I don't feel like doing 8 or 9 today, so I might have a lot to do tomorrow. Have a look to see if anyone's actually still streaming Append of Code. I mean, yeah, there might be. Some people just started now, I guess, if they're around the world. Bad Cop is still live? Has he been live since the problem released? I think he has. He's been on for hours. Let's have a look. Yes, wow, okay. Bad Cop is doing pretty cool streams because he's always trying to solve it in Bash, which is horrific, and I don't recommend anyone do that, but he does it so you don't have to. Wait, is he actually doing it, or is he doing something else now?
Solve for each tree individually.
He's doing something with ChatGPT. I don't think. Maybe he's finished the problem and just doing other stuff.
For a squirrel, you don't care which tree gave you the acorns.
But yeah, Bash, and he succeeds. I think he's solved every problem to date with Bash, which is absolutely crazy. This person is doing problem 9, which was what I was doing yesterday. All right, let's rate them. And I'll have to finish 9 tomorrow or whenever. All right, and after I take a short break, I'm going to come back with some San Andreas to cool down, blow up some helicopters, eat some oysters. Yeah, Imara, I guess that's one way to do it. I mean, it looked like my brute force was working, and then it got stuck on on line 14 or something, and just I don't think it would ever get past that. All right, thanks for watching. That in the end, that was actually a pretty good problem. I like that. I'll have to see what non Z3 solutions are. I have a feeling A star would work as well. Just it wouldn't be fast. It would probably take like 10-20 minutes or something. All right. See you next time.